So you just learned that now gravitational force isn't just like us falling towards the Earth. There's gravitational force in any two masses, right? Between any two things with mass. But of course, they usually show up when we have bigger masses. But why? Like, think about that. So far, in every other kind of force, there has to be some sort of contact, right? Applied force, tension force, frictional force. There needs to be contact between the two things that are experiencing that force. But then we get to gravity, and that just like all goes out the window. Like, these two masses do not need to be in contact for them to be a force between them. And that is insane when you think about it. Okay? So we came up, well, not we, you didn't, I definitely didn't, but physicists in history came up with this way of explaining why two things that are not in contact are still experiencing a force between the two of them. Because it's insane when you think about that. Like, that is really crazy. Two things aren't touching, yet they're exerting a force on one another. Like, that's really crazy. So we use this thing called fields. Okay? So what I need you to understand is so far we've been like very concrete facts. Not that fields aren't facts, but this is really just something that was come up with to describe how gravitational forces work. Okay? They're like, okay, well then I guess with mass, anything with mass has to have this gravitational field around it that pulls things towards it. And then, of course, the greater the mass, the greater the field around it is. So this is really more of an abstract idea, okay, than something that's concrete that we can see, that we can experience, things like that. So we're calling this a field. So gravitational field is just a sphere of influence, okay? So this is just something we use to explain how forces act at a distance, okay? So of course, a gravitational field is just its sphere of influence. Like, the Earth is the biggest gravitational field that we feel right now, okay? So remember, gravitational field is just how much force is being exerted on other masses per unit mass, which is per kilogram, right? So that's what a gravitational field is going to look like. So people do tend to have a harder time with gravitational fields because it's not this thing that we can experience or see or touch, or, you drop something, you see it fall, you see gravity at work, but the fact that there's a gravitational field then pulling that thing towards the ground is just not as tangible for us to think about, okay? So it's something it might take a little bit for you to wrap your head around. So remember, it's just us trying to explain why do two things that are not touching experience a force. Like, it really just seems nonsensical, okay? So gravitational field is the force that mass exerts per unit mass, okay? And it is a vector, of course, because we're talking about vectors. We're talking about forces and how much force per unit mass, and force is a vector, okay? But really, really important to note, gravitational fields, gravitational forces are not the same, okay? So, really important. So field lines for masses are always going towards the center, because if you think about it, a mass is always pulling you towards it, right? And then, of course, the bigger the mass, the bigger the field lines, which is why we're always falling towards the Earth, because it doesn't matter all the other masses around us. The field lines around the Earth are just so big that we're just all falling towards the Earth all the time, okay? So there we go. That's what a gravitational field is. Remember, they're always going towards the center of the object. That's really important because, again, direction does matter, right? So if I'm here versus if I'm over here, this is obviously not me because I'm not like wearing a skirt or a dress or anything. So let's do that. There we go. Now it's me. Now we can say it's me. So if that's me over here, well, the gravitational field of this big mass here is going towards the left, right? If I'm to the right of it. If I'm to the left of it, then the gravitational field is going to the right. So it depends on where I am around this massive object. I don't know what this is. It doesn't look like it's big enough to be the Earth compared to me, because I'm not that big. Okay, you guys. So I don't know what this thing is. It's a massive sculpture. It's the sculpture by the bow or something. I don't know. Anyways, that's why it really matters to know that field lines are always going towards the mass, because we need to then think about direction of the field compared to what you're looking at. Okay? So we have found a way to calculate this, because if you think about it, remember, it's force per unit mass. Okay, well, we can get that, right? That's newtons per kilogram. We can figure that out. Okay, so this is how we're going to do it. But there's two different ways to do it. So there's a way to calculate if you are the test object, the thing that's experiencing a bigger gravitational field, or if you're the producing object. So here in this case, I'm the test object. Test object. Okay? And then if we're looking at this guy, this is the producing object, right? Because it's the much bigger object that's pulling me towards it. Okay? So if you're talking about a really small mass that's experiencing the gravitational field, then that's the test object. And that's the one we've been using this whole dang time, right? Guess what? How do you rearrange this? Look at this. It's Fg equals mass times, oh my goodness. So really the whole time we've just been test objects experiencing the gravitational force of Earth. Okay, and that's actually how we find gravitational acceleration due to Earth, is we figure out the force and we can divide it by mass. That's not how we figure it out. What am I saying? We figured out how to figure it out when we were going over falling objects. But anyways, that is how we find the gravitational field. So lowercase g, not only is it acceleration, it's now this new fangled thing that we're going to call a gravitational field. Okay, so the units, meters per second squared, is actually equivalent to newtons per kilogram. And so that works out nicely for us. So again, if you are the test object, or if the question you're reading, it talks about a small object experiencing a bigger field. It's being accelerated due to a bigger gravitational field, then we're going to use this equation. Okay, so again, lowercase g now, in this case, doesn't just necessarily mean 9.81. That only means 9.81 if you were on the Earth, or if you're looking for the Earth's gravitational field, okay? But say I want to know something that's, sometimes if you ever put like a bowling ball on a mattress and then like a marble, the marble will go towards the bowling ball. So we could figure out that force and the mass of the test object and divide those, and then we have the gravitational field around the bowling ball. Okay, why do I need to put it into on a mattress? Because there's less friction, it's easier to move around stuff, and it's easier to like bend the space. Okay, and then that's actually more accurately showing us how things actually look in space, how they kind of bend space like that. Bigger objects. Anyways, I digress. So that's the small test object. If it's the producing object, what are we going to do? Then you take the g, gravitational constant, multiply by m, and divide it by r squared. What's r squared? Well, that's the distance from the center of the object to whatever point in space. Because that's the other thing, is the gravitational field is going to be a different strength depending on where you are in relation to it, right? If I'm right here now, I'm experiencing bigger gravitational space. I guess it's another day. I changed my dress and my skin. Well, that's weird. So this is going to be a bigger gravitational field here, okay? Not that, because I'm experiencing more gravitational force, right? So bigger gravitational field, and here we're going to have a smaller gravitational field over here because I'm further away. So it depends on where the object in space is, kind of where you're looking at your gravitational field from. Okay, so it's just, I know I've been talking about this a lot, but it's so important because I find people have a really hard time knowing when do I use this first equation versus when I use the second one. So remember, first equation, something small is experiencing a gravitational force due to a bigger object, okay? Number 2 can just be for any producing object. You're like, what's the gravitational field around this thing? Well, then I'm going to use the producing object one, okay? So just remember, these G's are not necessarily 9.81. That's only if we know that we're dealing with things accelerating towards the Earth, okay? So G here is gravitational field strength. So you have one of two options, okay? When we're talking about gravitational fields, you should put newtons per kilogram. But it's true that it's the same as meters per second squared. How do I know that? Remember, newtons is not actually a just a unit on its own. It's made up of other ones. What's it made up of? Remember, newtons is the measure of force. Force is mass times acceleration. What's mass times acceleration? Kilograms times meters per second squared. Oh, but if I do newtons per kilogram, look at that. What happens? There we go, the kilograms. So it's the same. Okay, so newtons per kilogram is actually the same as meters per second squared. We just tend to use newtons per kilogram when we're talking about gravitational fields, and meters per second squared when we're talking about something accelerating in a gravitational field. Okay? And so remember, r here is the radial distance from the center of the object to the point in space. So really, you can't just find something's gravitational field. You need to find it with respect to a certain point, right? If we're like, 10 centimeters away versus 1 meter away, it's going to be, the gravitational field's going to be different, okay? So let's just do an example of using this equation, okay, or one of these equations, and figure out what the heck am I talking about. So I'm given a diagram, and I want to find the net field at point P. What? First of all, okay, what? No. Net field at point P. Let's just figure out, what does net mean again? Oh, right, that means the sum of all the gravitational fields. Okay, first few things to remember. Gravitational field lines go towards the object, right? Okay, so towards the object. So first of all, P is to the left and right of all of these things. Okay, so when I'm looking for a gravitational field at point P, I'm only caring about what's happening in these gravitational field lines. Okay, so again, the gravitational field lines that are in the horizontal direction. Okay, so for this guy, it's going towards it. This guy next to P is going towards that one, but it's actually, that means it's going to the right, not the left. Okay, and this one closest to P is again going that way. Okay, so what am I going to do here? I'm going to ignore all these other field lines because right now I don't care about them. Point P is horizontally away from it. Okay, why don't I care about, by the way, this field line or this field line or this field line? It's because those aren't the ones that are closest to P in this interaction, right? So I choose the field line that's closest to P for each mass. So that's this guy, that's this guy. And for this one, this last one, when you're trying to choose between the two, this guy is the closer one. Okay, and that's also why we don't care about these field lines here. Okay, so that's kind of the clincher there, is I need to just focus on those field lines. So at point P, we have one gravitational field going to the left from mass 1. I'm going to call this mass 1, by the way. I'll call this guy mass 2 and mass 3. And then I have two gravitational fields going to the right. Okay, so then I know I have gravitational field due to the second mass and the third mass going to the right. Okay? And so that's how I'm going to find net field at point P. So remember, this does look like a lot like we were doing yesterday with the three masses, but we're finding gravitational force. So, and then a lot of people see a question like this and they try to find gravitational force instead of field. They're like, well, how do I know to find the field and not the force? Well, it says it in the question. Just thought I'd point that out. So I don't know what else to tell you guys. Like, it says find the field and not the force. So, there you go. The thing that sucks about field, though, like the variable that does represent it is g. It's a lowercase g. Like, what the heck does that have to do with gravitational field? I don't know. I don't know why it's gravitational field. Oh, maybe gravitational field, so lowercase g for that. But yeah, so a lot of people just look at FG and they're like, that's what I have to use because field's F. Yeah, no, gravitational field, G, lowercase g, okay? So again, this is a equation on your data sheet. It's under dynamics. It's under the force of gravity one. G, lowercase g is equal to gm over r squared, okay? So again, here I have no test object that's moving. I have a point in space. So if I have a point in space, I'm going to be using lowercase g is equal to gm over r squared. If there was a test little, mass here and it was moving to the right or moving to the left, then I'd be using that g is equal to force over mass, okay? But no, I need to use my, my g is equal to gm over r squared. And then again, net, what does that mean? It always means to sum all the whatevers. So in this case, we're summing the gravitational fields. Which direction should be positive? Got 2 going to the right and 1 going to the left, so let's make right positive. Okay, what does that mean? That means that I need to take gravitational field for 2 and add that to 3, but then I have to subtract the 1 from 1 because that is going to the left. Okay, so let's figure that out. Again, the equation is g times m divided by r squared. But I'm going to put m2 to make sure that I know that it's the gravitational field for mass 2. For mass 3, it'll be gm3 divided by r squared minus g times m1 divided by r squared. All these r's are also different because it has to be the distance between the mass and the point in space. This is the point in space right here with point P, okay? So we have these 3 meters here that's going to help us. So here's another thing I can do. I can actually sort of factor out a g because I don't want to write that 6.67 times 10 to the negative a million gajillion times. So I'm going to do this, okay? Usually I won't write this step, but I'll just do it here for you, okay? So I'm going to factor out this g because it just makes it so I don't have to write that annoying thing so many times, okay? Because it all has a factor of g. So why did I do that? Just because, again, now I only have to write this darn thing once instead of 3 times. Like, thank goodness for that. Oh my goodness. Yeah, it's a lot of work. Okay, so M2 is 10 kilograms divided by r squared. So remember, that's the distance between mass 2 and the point in space here. So that is just, look at that, 3 meters right there. Okay, so that's 3 meters. But we got to square it. Okay, plus m3 over r squared. So mass 3 is 30 kilograms. What is the distance between the 30 kilograms and the point in space? Look at that, it's 6 meters. Be careful about that, right? A lot of the time they'll just give you the distances between the masses. But if you need to cover 2 of those distances, so just be aware of that. So that's actually 6 meters. We'll square that. Minus m1 over r squared, so m1 is 20 kilograms. And the distance between m1 and the point of space is also 3 meters, as we can see from the diagram. Don't forget to square those. It's a very, very common mistake, so don't worry. Don't beat yourself up if you do. What do I get? I get negative 1.9 times 10 to the negative 11 newtons per kilogram. Okay, so this is actually going to the left. So I guess doesn't matter that there's 2 going to the right. The fact that the mass on the left is bigger and closer than the other mass that's really tiny, then it's going to the left. That's what's happening. So there we go. That is how you find net gravitational field at a point in space. Let's do one more example. So our next question is not doing this, but in 2 dimensions, although you will be expected to do that. So Don't let me lull you into a false sense of security. But I'm just not going to do it because honestly, it looks so similar to the one we did with forces, with gravitational forces. But now you're just using this equation, this gm2 or gm over r squared, rather than gm1 m2 over r squared, right? So again, that one, if it just says find the net field at point P, and you have two masses, but they're at different points, and point P is right here. And of course, this one's in the x direction. This one is in the kind of x and y. So you, again, find the gravitational field for this one, and then break it up into x and y, and sum in the x, sum in the y, Pythagoras, tan, do all that, okay? So it looks very, very similar, but in that case, you're looking for net field, okay? And so remember, usually when it says at point P, it's just a point in space. There's no mass here at point P. So that's another tip off, that you're looking for the field and not the force. So what we're going to do is I'm just going to show you how we can use both of the equations depending on what we have. Okay, because remember, we were given two equations to find G, our gravitational acceleration or our gravitational field strength. So we want to determine the field strength of a region 14,000 meters off of Earth's surface. If a 3 kilogram object experiences a force of 29.3 newtons. Okay, wait, we're given a lot of information here. We're given the distance. Actually, we're only given the distance from Earth's surface. We're given the mass, and we're given the force it experiences. So, it's a small thing and it's experiencing a force of the Earth. Oh, well, that sounds like we can do this guy, can't we? Okay, why is G not just going to be 9.81 here? Because it's 14,000 meters off of Earth's surface. So once you're that far off of Earth's surface, no, you're definitely not experiencing 9.81 again, okay? So here we are going to calculate, but we have FG, we have the force of gravity that this small object is experiencing, and of course we have the mass of the small object. So let's just do that. It looks nice and easy. So again, it's experienced a force of 29.3 newtons. We're going to divide that by 3 kilograms. And we get, what do we get? We get 9.77 meters per second squared. So that's actually still not that different from 9.81. So that's pretty crazy. That's what, 14 kilometers off of Earth's surface, and it's still only 9.77, which is why when you guys put on your labs that, source of error is that gravitational acceleration is going to be different from the second floor to the first than the first. That's why I laugh. Because sure, you're right. It might be a teensy bit less on the second floor, but definitely not enough to make any sort of calculation error whatsoever. So still 14 kilometers off of Earth's surface, the acceleration due to gravity is barely changed. Okay, so it's important to keep in mind. The thing is, we actually were given enough to use this other equation as well. Let's take a look at it again. So the thing is, this M is talking about the mass of the Earth. It's not talking about the mass of the object. Because remember, this is for the producing object. So here we care about the thing that's producing the big gravitational field that the thing is experiencing force of. So there we go. That's the mass of the Earth. So at first you're looking at this and going, we don't have that. We don't have the mass of the Earth. Again, look at that data sheet of yours. When you look under constants, it gives you two really important things underneath the gravitational constant. It gives you the radius of the Earth and the mass of the Earth. Wait, do we need the radius here? Do we? I think we do, because guess what? We are given the distance off of Earth's surface but we are not given how far we are from the center of the Earth. Remember, when I'm doing this, I need the distance from the center. Okay, so if here's the Earth and here's 14 kilometers off of it, I was only given that length, okay? I need the whole length to its Oh, that doesn't really look like a straight line. I need the whole length to its center. Okay? So that is something that we have to keep in mind. So we need to, for our radius, take this 14,000 meters and add it to the radius of the Earth, which we also have, again, on our data sheet. So we have all of this. Okay, why am I showing you this? Well, so I can show you that their data sheet has these values that we need, but also just to show you, in this case, I can find it out both ways, and I'm going to prove it to you that I get the same answer. Okay? So G is 6.67 times 10 to the negative 11. I told you don't have to memorize that, but you're going to have it memorized by the end of this unit just because you're going to be using it so much. Mass of the Earth, according to our data sheet, is 5.97 times 10 to the 24 kilograms. That's pretty darn heavy. And then divide that by r squared. So remember, what's r? The distance from the point in space to the middle of the Earth. So remember, that was the 14,000 meters plus the radius of the Earth. The radius of the Earth is 6.37 times 10 to the 6 meters. Okay. So we're going to add those together. We don't forget to square it, please. It's honestly the most common calculation error is just forgetting to square something. So be really careful with that. When you plug that into your calculator, you get, guess what you get? You get 9.77. Who could have guessed? Okay, and I'll put this one in newtons per kilogram because, I mean, why not? Because that's the unit. I did the other one meters per second. You see that? I'm sneaky. Can put meters per second squared, newtons per kilogram. Again, typically we put newtons per kilogram when we are talking about gravitational field, but I'm not gonna take off marks if you put meters per second squared because, again, you already have enough chances to lose marks in other places on your quizzes and your tests. So I'm not gonna do that to you. I won't. But yeah, so there we go. That is gravitational field strength and how we find that. But again, it is so difficult to know when to use what equation. So remember, G equals Fg over m. That is when we have a small object experiencing a bigger gravitational field. G equals GME or GM over r squared. That's when I'm trying to find the gravitational field of the producing object. And in this case, that mass was not the little object that's experiencing a force. It was the big object that is creating the really big gravitational field. Okay? Good luck. Have fun. Hope I didn't just break your brain or anything.